dive. Today, we're diving into something pretty fascinating sent in by you, our listener. We've got this high degree polynomial equation, a ninth degree beast, actually.
Yes, quite the challenge.
And our mission really is to explore a method proposed in this document, C91.pdf, for trying to find its roots.
Absolutely. And when you first look at it, something like px plus pa, well, it goes on.
It does. All the way to minus 253,846 equals 0.
Exactly. Px plus 1 Virgo plus the plus 3 plus we or it looks intimidating.
Definitely. The source material gets into some pretty advanced algebra specific formulas.
It does.
Okay, so let's try and unpack this without, getting totally lost in every single calculation.
Good idea.
The aim isn't to replicate the whole thing by hand, but to really grasp the core idea, the approach the document takes, and the sort of key steps.
We can highlight the main values, the main formulas, like landmarks.
Exactly. So, the expedition today, understand this polynomial and the suggested method for finding its roots.
Right. So that polynomial again, px, pia plus ha, olio plus our, odur plus odur, o.
Plus,
The source gives a general form too, right? To help see the pattern.
yes, it lays out a template. P plus E plus OU plus UA plus AU FU plus UB plus U without AQ plus AU by OI2 plus E20 over 88 plus 88.
Think of these things as placeholders for the numbers, the coefficients in our actual equation.
Precisely, and the document tells us what they are for our specific polynomial.
Okay.
So OP minus 1600 money 10, OK minus 67572.
Okay, Lexi's 1. That one's small.
Yeah, relatively. Then low key minus symmetry 601 618.
Getting bigger again. LEQ is minus 1536592. LUQ is back to 1. And finally, O0AT by 820 by 880AQ is 253826.
So those are our starting ingredients based on the source.
Exactly, those LQ values.
Okay, we have the polynomial, we have these LQ building blocks. Now the document brings in a specific method attributed to Mourad, Sultan, Ezouidi, H.
That's the one mentioned. It's presented as the tool to use
The
here.
official key for this lock, maybe.
You could say that. And the document applies it systematically. It calculates these expressions for different values of k, starting at k0 and going right up to k9.
Okay, so it's a step-by-step process using this HUSM formula.
Right. And those calculations involve binomial coefficients. The numbers from Pascal's triangle, essentially.
Oh, right, combinations. Those show up in the source with those triangle arrays.
Exactly. And they're combined with our HEO values.
So how does that look in practice for K0, for instance?
Well, for K0, the document shows a calculation for something it calls C as here. Now, we won't wade through every summation symbol and C, A, T, E, and K here.
Probably wise.
But the key takeaway, according to the source, is that when you plug in the relevant ILA values and binomial coefficients for K alone, this CSR value comes out to 0.
0. Interesting. So the first step yields 0.
Yes. And then it does a similar thing for K1, calculating something called CC.
And for K2, CCSR. Let me guess.
All 0. CCs and CCSR are calculated to be 0.
Huh. So the first 3 steps using this method seem to zero out.
That's what the document indicates. But it doesn't stop there. It continues this process for all K values, right up to K9.
Okay.
So K3 gives CCCSR, K4 gives, well, you get the idea. Each step uses the same kind of logic, applying the formula with the L values. It's methodical.
A bit repetitive, perhaps, but structured.
Very structured. And even though we're skipping the blow by blow, the document eventually presents the final results of all these KLO to KO9 calculations.
They're all values.
Yes, SR through 0 by E, 20 by 8, 20 by 88 are the outputs of that whole process.
And what are they? Are they all 0?
Not all of them, no. According to the source, S0R equals 0, S0 is 0, S0 equals 0, 0. So far, so good.
Okay.
But then SCR is 683,999,482,673.
Whoa, okay. Definitely not 0. That's a huge number.
It is. Then S0R is 0R is 0, 0, 0, 0 is 0, 0, 0.
Right to zeros.
Then S0 is the same huge number. 683,999,482,673.
Really? The same value for SR and SR is interesting.
And finally, 0 SE20 by 820 by 88 R equals 0, 0.
Okay. So we started with the LQ values from the original polynomial. applied this HSM method step by step from K0 to 9 and ended up with this new set of SSR values, most of which are 0, but 2 are this enormous number.
That's the result presented in the document, yes.
The next move is to use these SSR values to build a new polynomial, hopefully a simpler one.
Okay, it makes sense.
The source shows this new polynomial form. Px, xs plus xs xs plus sxis plus xr plus r plus sx plus xso plus xsr plus xx, right? What?
And now we plug in, values we just found. Exactly. And since most of them are 0,
a lot of terms just vanish.
Precisely. We're left with px, xor, xw. Then the xi, xa, 0 terms are gone, plus SR times XOR.
So XR plus 6839994826736.
Right. Then xi, xo, XOR terms are gone, plus S0 times xx.
Which is the same huge number again, plus 6839994826736.
And the last term, 0x3.22673 is 0, so equals 0.
Wow. Okay. Px x it's plus 6839994826736 plus 6839994826736 equals 0. That looks much, much simpler than where we started.
It really does. A lot less intimidating.
So can we solve this one?
Well, we can start. The source shows the first step is to factor out an x.
Yeah, because every term has at least one x, so x times.
X times x plus 6839994826736 x 0 plus 6839994826736.
Okay, and that immediately gives us one root, right? If that whole expression is 0, either xa
or the part in the parentheses is 0. So yes, xa is one root of our original polynomial. Found one.
Nice. One down. So now we just need to solve x0 plus 6839994826736 echo plus 6839994826736.
Correct. That's the remaining challenge. Still looks tricky, an 8th degree equation.
Yeah, but notice it only has xeo and xos terms. That looks like a quadratic equation almost, but in terms of xs.
Exactly. It's what we call a quadratic inform or a biquadratic equation,
right?
Extended. If you think of y xeo, then it's y plus 6839994826737y plus 6839994826737.
Okay. The document seems to take a slightly different path, though, introducing some q prime terms.
It does, yes. It brings in an equation, xeo plus EOCE.
Which simplifies because sesEO was 0, so presumably sesQ is treated as 0 here, too.
That seems to be the implication of the source leading to xx plus SEO is 0.
Okay.
And then it gives a value for SKO. It says SSS1 7604337484153.
Another massive number.
Yes, and it notes that this is approximately 13,116,530.592.
Okay. How does that help us solve the x equation?
Well, the document uses this value along with SES-R to find values for xs. It presents the formula. X over is 2.
I see. It's like using the quadratic formula, but for finding xeo, using sesEO and the sesEO related value.
Kind of, yes. So plugging in the numbers, xeo 6839994826737. Sure, 7720-433-748-41533.
Right, and the square root part is roughly 13,116,530.59. Oh wait, no, the source says XOR is the square, so the square root is just 13,116,530.59. Let me recheck the source.
You're right. The notation is a bit dense. It seems to calculate XEO. It uses SER 68399948223. Kimono Stereo. It uses 68399482673 and the SEO33. SEO 720-437-484-533, which is indeed about 13,116,516.59. Thus, the source uses SES0 1320 and so down. This seems inconsistent with the earlier SES value. Let's proceed with the value shown in this specific calculation step in the source, acknowledging the apparent discrepancy from the previously listed SER.
Okay, proceeding with the value shown in that step of the source, XEO 132204443 figurine to SEO 17748415332.
Which is roughly 132204441 of SEO 4483 first 443.53.
Right, and calculating those two possibilities gives two approximate real values for XEO.
Yeah, okay, what are they? Approximately 131,68472.80 for the plus case, and 518042.80 for the minus case.
So we've boiled it down to XO equals roughly 13 million something, or X0 equals roughly 52,000 something.
Correct. Those are the two key values obtained at this stage.
Now we just need to find x, right? We need the fourth roots of those two numbers.
Yes, and since we're looking for roots of a 9th degree polynomial originally, we expect complex roots too. The source uses a formula involving e to a complex power.
Right, the complex exponential form.
Exactly. It gives a general formula for the roots nodo a 10 I8 ba8 xbc as value of xouq2. This finds the roots spread on the complex plane.
Okay, taking the fourth root. Wait, the formula in the source shows the fourth root of the absolute value of xo, written as value of xo, and then e to the power of key 2, where x goes from 0, 1, 2, 3.
Yes. The fourth root notation there is slightly unconventional, but it means taking the principal fourth root. This formula finds 4 roots for each of the XO values.
Giving us 8 roots so far, plus the XO we found earlier, that's 9.
Almost. There's one final adjustment mentioned in the source. It incorporates the term LUQ9.
LUQ was 18, so 18,9 equals 2.
Right. This value of 2 is added to the roots found using the complex exponential formula, giving the final roots, which the source calls AE10, A10, AEK, XBC.
So the actual roots are shifted by 2.
That's what the final formula suggests. We get 2 sets of roots.
Okay, what do they look like?
The general forms given are E10, EPC10, HB80, XBC, Phi4, 1, 2, 3, coming from the smaller XEL value is 2 plus, fourth root of 51942.2, AKA29, and the other set.
Also for K is 0, 1, 2, 3.
Yes, coming from the larger XEL value. HB10, XB80, XBC equals 2 plus, fourth root of 131,684.72.89. The source also explicitly states a KA10, XB80, XBC equals 2 as a root, which likely relates back to the ATEQ somehow, perhaps via the transformation, though the connection isn't fully elaborated.
Okay, so that gives us the general forms for the 9 potential roots based on this method. Wow, what a journey.
It really is. We started with this very complex-looking 9th degree polynomial.
Yeah, daunting.
Then we followed the steps outlined in the source, using this method attributed to Mourad, Sultan, Ezouidi, HSC, calculating intermediate values, the R's,
which involve those binomial coefficients and the initial OQs, a very systematic, if lengthy, process.
And that process led to a much, much simpler polynomial.
Yeah.
XOMO plus big number, XAO, same big number, X equals 0.
From which we got XOs as one root immediately.
Right. And then tackled the remaining XA equation by treating it like a quadratic in XO using those Q prime values from the source.
Leading us to 2 values for XO.
And finally, using complex exponentials and that final shift by 2 XOU9, we arrived at the general forms for the 9 roots.
It's quite a demonstration of, well, advanced algebraic manipulation.
It certainly is. This deep dive really just gives you a glimpse into the kind of techniques that exist for solving these high-degree equations. The source presents one specific methodology.
And it shows how something seemingly intractable can be broken down, transformed into something solvable step by step.
Though the steps themselves require careful calculation and understanding of the underlying theory, it's not trivial.
No, definitely not. It makes you think, though, what kind of real-world problems actually lead to equations like this? 9th degree.
That's a great question. You might find them in complex system modeling, perhaps in physics, theoretical engineering, maybe even some areas of economics or signal processing where intricate relationships are involved.
Fields where many factors interact in complicated ways.
Potentially, yes. And it also makes you wonder what other mathematical tools are out there. This Heism formula is one approach presented here, but mathematicians have developed various numerical and analytical methods over the centuries.
Right. Are there completely different ways to attack this same problem? Probably.
Almost certainly. Different methods might have advantages in different situations. Maybe some are faster computationally, some give more theoretical insight.
It's a fascinating area. The quest to solve equations is so fundamental to mathematics. Definitely leaves you with something to ponder the sheer complexity that can arise and the ingenuity needed to find a way through it.
Indeed. The power and sometimes the surprising elegance hidden within these complex mathematical structures.